Welcome to Series Lesson 5, the ratio test. Okay, so for our warm-up today, remember we did write the general term and the term after the general term. Okay, so this is really just 1 over something, and that something is always 1 more than the position you're at. So if this is the first number, and this is the second number, and this is the third number, and this is the fourth number, and this is the nth number, then the bottom is really just n plus 1. If you really couldn't figure that out, then you could have done this. 2, 3, 4, 5 is an arithmetic sequence with first term 2 and common difference 1. This actually comes out to be, guess what? N plus 1. How about that? So you could actually use this formula to get that denominator. That's an arithmetic sequence technically going up by 1s. So just use 2 plus n minus 1 times 1. Okay, there it is. And the term after it, of course, would be called a sub n plus 1. And that's just basically the next term. So it would be 1 over n plus 1 plus 1. How many of you got number 1 right? Okay. Next one is 2 plus 1 over 3, 4 plus 1 over 9, 8 plus 1 over 27, etc. So some people get really good at this kind of stuff, and they realize that this is like 2 to the first plus 1 over 3 to the first. And this is 2 to the second plus 1 over 3 to the second. And this is 2 to the third plus 1 over 3 to the third. So those students usually get them right away, and they're like, oh, okay, it's just 2 to the n, add 1 over 3 to the n. So some people can do that. If you can't do that, you can follow this green here instead. 2, 4, 8 is a geometric with first term 2, common ratio 2. First term 2, common ratio 2. So that'll give you the 2 to the n that you need here. And then the purple is the denominator here. 3, 9, 27 is a geometric with first term 3, common ratio 3. This will give you the 3 to the n down here. So if you really need formulas, you could actually use them. Okay, but the next term would be found just by simply replacing any n's with n plus 1s. So this would be 2 to the n plus 1 plus 1. And this would be 3 to the n plus 1, like so. So what do we mean by a sub n plus 1? We mean the next term. You just simply add 1. Is it the last term? No, the series goes on forever. But these are 2 terms. One that's called the general term, and then the next one after it. Number 3, this one has the negative, positive sort of look to it. So there's that one, negative. This one says 4 times 2 over 9 minus 1. This one says 8 times 3 over 27 minus 1. And I gave you one more just so you can see the pattern clearly. 16 times 4 over 81 minus 1. Now if I had simplified these to like negative 2 over 2, 8 over 8, 24 over 26, that's when it gets really hard to pick out the pattern. But by separating it like this, you can see sort of the progression. And I have an extra parentheses on my 16 times 4, which I don't really need. So I'm going to get rid of that real quick. Okay, I think I copied that right. Okay, did you guys figure out that the 2, 4, 8, 16 is really just 2 to the n? Okay, so we have a 2 to the n. And then there's times 1, times 2, times 3, times 4. So that's times what? N. And the bottom is a 3 to the n, take away 1. So that's the n plus, that's the nth term. And then what's the next term after that, class?
Wait, hold on. What about showing the...
Oh, the alternating. Yes, we got to consider the alternating signs. So how are we going to make it go like negative, positive, negative, positive? You can use negative 1 to the n, or you can also use cos pi n. That was from our last lesson, Friday. So you can put in a little cos pi n here. or a -1 to the n, your choice. They do the same thing. Okay, I'm going to choose -1 to the n just because it's more common. Okay, question. Did anybody try to combine this into -2 to the n times n over 3 to the n minus 1? Because you could do that too. You could actually take the -1 to the n times the 2 to the n, and put those together and call it -2 to the n. You're allowed to do that. Did anyone write it that way instead? Okay. Well, in any case, your next term is going to be just this with +1 inserted for each, or after each n, right? So here's your next term. It's -1 to the n plus 1. It's 2 to the n plus 1. It's times n plus 1. And it's all over 3 to the n plus 1. Take away 1. That's the next term. Okay? And then the last problem for warm-up was 1/2 minus 3/4 plus 5/6 minus 7/8. Okay, so some people, like I said before, are really good at this, but 1, 3, 5, 7, let me color code. 1, 3, 5, 7 is just an arithmetic sequence. 1, 3, 5, 7. This is like an A series, arithmetic series. And it just basically starts with a 1, and it goes up by 2's. So you could actually write the top of this as 2n minus 1. The bottom is 2, 4, 6, 8, who do we appreciate? Which is first term plus n minus 1 times 2, if you're using like a little arithmetic formula. In other words, it's just 2n, which is obvious in retrospect. But that's your nth term right there. We circle it. And the next term would be, question? Yeah, I'm missing the oscillator again. Let's use, I forgot my oscillator. Let me put the oscillator in. Alternator. Oscillator might even be a better name for it. Okay, so oscillator, let's stick that guy in here. -1 to the, okay, I don't want to use n. I want to use like n plus 1. That way, -1 to the n plus 1, that'll give me a positive first, and then negative if we start with n equals 1. Thank you, Hunter. Okay, and then the next term would be -1 to the n plus 2. What comes after 2n minus 1? This is kind of tough. Obviously, the bottom is just 2 times n plus 1. What comes after 2n minus 1? What's the next term? 2 times n plus 1 minus 1 would be next, right? What does that give us? No, 2n plus 2 minus 1. 2n plus 1 comes after 2n minus 1 if you're counting in odds. So, for example, if you plug in 50, right? If you plug in 50, you get 100 minus 1 and 100 plus 1. Those are two consecutive odds, 99 and 101. Okay? All right. So that one was a little awkward. But there you have your n and your n plus first terms. Okay, I'm going to pause the recording, see if you guys have any questions on worksheet 3, which is due today. Okay, guys, so I don't want to spend too long on this lesson because it's really not a difficult idea. It's one formula. I will say this is the last test I'm teaching you, but it isn't the last test every teacher teaches. There's another one called the root test. But I'm not going to teach it because, first of all, in my experience, most of the problems that can be done with the root test can also be done with the test I'm going to show you today. So I'm not going to teach the root test because it's a little bit extra for most problems. Also, I've never seen a root test problem with an AP exam. So although I have seen it in some practice books. Anyway, the ratio test is going to be the new test of the day, and it's kind of a go-to test that you're going to really like. I think you're going to like it a lot. Okay, so just a quick review. What have we used so far? We have a rule called nth term divergence test. It basically says if the limit isn't exactly 0, forget about it. It diverges. Okay? All right. It cannot help us determine convergence, though. The second thing we learned was the integral test. The integral test is the test that actually helped us decide that the harmonic series was divergent. If you go back in your notes, you'll see that I proved that 1 over x diverges as an integral, therefore 1 over n diverges as a series. That's a great go-to, but it has very strict rules. No negatives ever, in your series. And also, are you that good at integrating, really? That's a question I would ask. Am I going to use this test often or just sometimes? The next test we learned was the DCT, where you compare a series to a series you've already studied, like a G series or a P series. And then the next one we learned was the limit comparison test, where you're comparing two series, okay, to see which one grows faster. Or, I'm sorry, you're trying to compare two series with the expectation that maybe they grow the same. So, all of these have different outcomes. But there's a new test called the ratio test, and what I like about the ratio test is it feels like a formula, which is nice. And second, I like it because it compares the series to itself. Okay? It's the only test we have so far that compares the series to itself. So watch this. Here's the ratio test. If LIM, n goes to infinity, of absolute value n plus first term over nth term is equal to L, and L is less than 1, then we have convergence. In fact, it's absolute convergence. If you were here Friday, I'll write that in right here. If L is greater than 1, or if it's infinite, then it's divergent. I'll go ahead and write the adjectives here: convergent and divergent, not the nouns. Okay? Which means I need to now make this an adverb. Absolutely convergent. Wait a minute. That green word is modifying an adjective. Is it still called an adverb? I don't know.
It's an adverb.
Adverbicative. Okay. Don't quote me on my amazing English skills. But anyway, if L is less than 1, it means absolutely convergent, and if L is greater than 1, it means divergent, and that includes, of course, infinity. Now, if L is equal to 1, actually, unfortunately, our wonderful go-to test has failed us. We don't glean anything. Isn't that a great word? From this test. Yeah, you don't get any information from this particular test if you happen to get 1 here. So this is called the ratio test. You're going to like this test. You'll use it probably the most of all the tests. Unfortunately, if all your hard work leads you to get 1 in the end, then it means you need to go try a different test. Because this test, literally, if you get 1, we have no idea still whether the series converges or diverges. It literally is inconclusive, completely inconclusive. So try another test. Glean is a beautiful word. Okay, we're ready to try out this new test. We've already done 4 warm-up problems where you wrote down a sub n and a sub n plus 1. That's what the warm-up was about, just trying to get you to write down a term and the term after the term. Okay? So our first example is sigma, how about that? N squared minus n plus 1 over 2 to the n. Now you could try this problem using any of the other methods I taught you, but I think you find it to be a pretty challenging problem, actually, from any of the perspectives we've already taken. Okay? For example, with DCT, it's a little hard to compare to other things. LCT, those limits are awkward sometimes. Let's try our new test. Maybe there is another test that's not too bad, but let's try our new test. Our new test says this. Since this is a sub n, we're just going to jot down a sub n plus 1 real quick. Okay, so that's going to be n plus 1 squared minus n plus 1 over 2 to the n plus 1. I just replaced all my n's with n plus 1's. Now I'm going to take that and put it over the original a sub n. So this is Mr. Ugly. It's the n plus first term. And we're going to put it over Mr. Clean. And you thought the original problem was bad. Look at the n plus first term. Okay, don't forget this absolute value here. It is part of the test. Before you freak out and say, man, I wish that wasn't there, that just makes things more complicated. Actually, it's nice because if there are any alternators in the series, they are now destroyed. So, do you see a cos pi n anywhere? Not on this problem. Do you see a negative 1 to the n anywhere? Not here. But those could physically be erased from the problem at this point. Okay? That'd be nice. So it's actually nice that there are absolute values here. Now what we have to do is evaluate this limit. Oh, yuck. Okay, let's clean it up a little bit. For example, some of this stuff just cancels out algebraically. So this will take me a few steps because I'm not trying to go too fast here. The top here is n plus 1 squared minus, and then right here there's a minus n minus 1, but then we're adding 1. So basically this is just minus n. So all I did on that step was I just canceled the minus 1. This is a 2 to the n on the bottom. Okay, then we have the whole ID on rule where the inner is the denominator and the outer is the numerator. So let's put that into effect. So we have n plus 1 squared minus n over 2 to the n plus 1. Actually, I'm going to do multiply by reciprocal instead. You can do it either way. You can use ID on or multiply by the reciprocal of the bottom fraction. Okay, some things are going to cancel out here too. So these are a little bit heavier on the algebra. But whatever this comes out to, we have an instant answer. Converge or diverge, so that's cool. Yeah, Hunter?
Would 2 to the n and 2n plus 1 cancel out to equal 2?
Yes. So I actually just, right when you're asking that, I actually wrote something that will help us with that. First thing I did was I foiled the top left. I foiled this out to be n squared plus 2n plus 1 minus n. And then the other thing I did was I rewrote 2 to the n plus 1 as 2 to the n times 2 to the first, also known as 2 to the n plus 1. So what happens here is the 2 to the n cancels out. That's nice. Which means we've got this thing down to a polynomial over a polynomial, right? So this is actually going to be really easy now to finish. We have n squared plus n plus 1 over, careful, we've got to distribute it too, 2n squared minus 2n plus 2. This is easy. It's just a half. And we have a full conclusion. We're done. It's convergent. Greatest terms here are n squared and 2n squared, right? So I'm just taking the leading terms, top and bottom. So the cool thing about this test is when you're finally done with this work, you're done with the whole problem. You have absolute convergence. It's absolutely convergent was our conclusion. How about that? That's pretty cool. So it's one test. You're actually testing a series with its own self. Let's think about what this is. It's really kind of clever. I like it. It's clever. Look, what you're saying is this. It's all very logical, really. What you're saying is that when you divide this by this, okay, don't miss this logic, okay? When you take this and divide it by this, it gives you a ratio less than 1. Well, of course it does. The terms are all diminishing, remember? If they weren't diminishing, we would have already proven divergence by the instant divergence. All of the series we're studying get smaller as we go. But here's what we're saying. We're saying that this happens forever. So we're taking this and putting over this as an expression, and we're showing that this ratio is is less than 1 in the infinite case. This proves convergence instantly. It's extremely clever, actually. This test is probably the cleverest of them all. Although it's a little hard to understand why it works.
Maybe. Would it work if you did a n plus 2 over a n plus 1?
Sure, yeah. And it would certainly be true for a n and a sub n minus 1 will turn to 4. So you could do it that way too, although I've never really seen anyone do that. So take the nth term and the n plus first term, put them in ratio, do the limit, make sure there's absolute values. That'll kill off the alternators though. And then you've got proof of divergence or convergence instantly. The only time this rule fails is if you happen to get 1 in the end, and then you just kind of have to go back to the drawing board and start the whole problem over again. Use a different test. Let's try this one now. You're going to like this one because the uglier the problem, the more fun it is to cancel everything out. Okay? So you'll see that the ugliest of the ugly problems, so many things cancel out. It's very rewarding. My second example I picked, and I would give credit where credit's due, but I don't remember who it was from. It might be from MITe or Larson. I just don't remember. But look at this horrible problem here. Oh, by the way, Chloe asked earlier about the 1 over n factorial. The ratio test shows us instantly why that thing converges. So if you know the ratio test, Chloe, last night, and you had run into that number 7, you would have definitely used that. I always use ratio test anytime I see a factorial. Okay? But let's look at this problem. Which is bigger? N times n times n times n times n times n times n forever? Or n times n minus 1 times n minus 2 times n minus 3 times n minus 4 forever? Oh. Sounds like this is going to diverge. So how do we prove that? It's kind of awkward. We kind of just verbally did. N times n times n is term by term greater than n times n minus 1 times n minus 2 and so forth. But watch how nicely the ratio test handles this problem. So the first thing is you have to understand that this is your denominator. This is your a sub n. A sub n plus 1 is just the exact same thing, only it has n plus 1s for every n. Okay, so it looks like a sub n. Now let's put these in limit with each other, in ratio with each other, excuse me, and then take their limit. So big fat fraction. We're going to put Mr. Ugly on top. That's important. Don't ever put the original function on top. You want the n plus first term on top. So what's scary about this problem is the factorial maybe, but that's going to go away in about 2 seconds. Okay, so watch close. This is a very important idea, and it's not just for this lesson. N plus 1 to the n plus 1 means n plus 1 times n plus 1 times n plus 1 n times, and then one more time. So it's a lot of n plus 1s. So I'm going to write it as n plus 1 to the first times n plus 1 to the n. That is exactly the same thing as n plus 1 to the n plus 1. N plus 1 factorial literally means n plus 1 times 1 less than that. N. Times 1 less than that, n minus 1. Times 1 less than that, n minus 2. In other words, n plus 1 factorial is the same as n times n factorial. N plus 1 times n factorial. So this is a little bit hard to grasp at first, but it's the same. What I just did was I just changed this purple to this. It's like saying 6 factorial is the same as 6 times 5 factorial, which you guys would all agree with. Isn't that true? And 4 factorial is the same as 4 times 3 factorial. So n plus 1 factorial is the same as n plus 1 times n factorial. Okay, and then on the bottom here, we have n to the n and n factorial. And this is the fun part. Goodbye n factorial. Even the n plus 1 cancels out. I'll color code. So the blues canceled out and the greens canceled out, see? Maybe that wasn't as fun for you as it was for me. But here's where the problem gets really cool. Check this out. We have n plus 1 to the nth over n to the nth, which in turn can be treated as n plus 1 over n, all to the nth, which in turn gives us LIM, n goes to infinity, 1 plus 1 over n to the nth. I just kind of took the n over n and the 1 over n separately there. And this is E, yes. The answer to this problem is E. Good eye, Hunter. Good eye. That's the definition of E. You can't see what? Can you see the whiteboard?
I can see it.
This big white thing right here. Okay. You might not know why it's E because this is where E came from. So why is this coming out to E? It's because that is E. Actually, one of the definitions of E is this. So why is this E? It's because that's E. It's not, there's no reason. That's just what it is. It's defined that way, even if you can't see it. Okay. Anyway, what is this value? Is this greater than 1, or is this less than 1? We haven't drawn a conclusion yet. Greater than 1. So some of you suspected divergence on this problem. We've just proven it. Therefore, let's actually go ahead and write a sentence here so we have a good conclusion for the day. So here's what we're saying for this problem. Sigma n equals 1 to infinity, n to the nth over n factorial diverges simply because the limit as n goes to infinity of a sub n plus 1 over a sub n, absolute value, is E, which is greater than 1. There's a nice little sentence for you. Actually, the ratio test is more than a go-to. Listen, don't miss this. Without the ratio test, we cannot handle 2 more ideas this year. Radius of convergence and interval of convergence. We will not be able to do them without the ratio test. So it's actually a tool that we'll use later too, and we'll be glad we had it at that time too. This thing will handle the ugliest of problems, including was the factorial, because what's happening is you're comparing the series to itself. So no wonder you're getting so much cancellation. Beautiful. Okay, so this is conclusive and it's divergent. If you get 1, what do you do? If you get exactly uno, what?
You don't glean anything.
You glean nothing. You glean nada, which means you're going to have to do what?
Another test.
That can be frustrating. You work so hard on the ratio test only to find you wasted all that time and you have no choice but to try something else. But it doesn't happen often.
What do you say when that happens, Mr. Short?
I say,
Say it.
oh, what do I say when that happens?
Say it.
I say, oh man.
Oh, no, you just said you're bad.
But see, I thought you're bad meant you're good. I'm so confused. And then I'm good means I don't need anything right now. It's like, would you like a popsicle? I'm good. It's like, what are you bragging about? I asked you if you wanted a popsicle, for crying out loud.